Hi everybody, in this video I want to talk about another application of the logarithmic scale of things, and what I want to talk about is the idea of sound intensity measured in decibels, which is our unit for measuring sound intensity. Well, the dynamic range of human hearing and sound intensity spans from 10 to the power of negative 12 watts per meter squared to about 10 watts per meter squared. This means that the highest sound intensity that can be heard is 10 trillion times as loud as the quietest, okay? So when they say the highest, they mean the loudest. This span of sound intensity is impractical for normal use. In other words, if we were trying to put like the various intensities on the y-axis of a graph and compare various sounds, we would find that the scale of difference would be so massive that it would be impractical to fit on the graph, because our scale would have to have differences that would range by a factor of 10 trillion times if you were comparing the sound intensities, right, of two different I guess noisemakers, for lack of a better word. But so a way that we can handle this, though, is we can kind of like take that exponential relationship that exists in terms of the ratio of intensities and pare it down to a logarithmic scale. So a more convenient way to express loudness is a relative logarithmic scale, with the lowest sound that can be heard by the human ear, which we could say is intensity 0, which would represent 10 to the negative 12 watts per meter squared. And we give that a measure of 0 decibels. And then, if we give that a measure of 0, then we can work from there. And we can use a formula that you see right here called the loudness of a sound is equal to 10 times the log of the ratio of the intensities of their sounds, okay? And measured as I over IO. Okay, where L is the loudness of the decibels, I is the intensity of the sound being measured, and IO is the intensity of the sound that is basically on a 0 decibel level. So what you see on the table on the right here is you see various decibel readings of sounds that a human might hear, right? Normal conversation has a decibel level of 60, subway 90, screaming 100. I guess it depends on who's screaming and what they're screaming about. Rock concert 120. A jet engine, if you've ever been near to a jet, is very loud. That's 140 decibels. And a space shuttle launch 180 decibels. Okay, so extremely loud. So this brings us to a typical type of logarithmic decibel question, which is how many times more intense is the sound of a rock concert compared to that of a subway? So watch how we do this. What we do is we just apply our formula, and it's really a fairly straightforward proposition. What we'll do is we will move up the page a little here, and we'll say, well, a rock concert would produce a decibel reading of 120. So it's loudness. So we'd say 120 is equal to 10 log I over IO. Okay, and then we would go ahead and we would try to simplify this expression in such a way as to get a pared down or easier representation of the scenario, right? So doing that, what we could do is we could divide the right side by 10 and divide the left side by 10, and what this would leave us with would be 120 divided by 10, 12 equals log base 10 I over IO. And so what we would say then is we would say this could be written as exponential. We could say that 10 to the power of 12 is the relative intensity of the rock concert compared to a sound of 0 decibels. In other words, the rock concert is 10 to the power of 12 times more intense in terms of its sound output and intensity than a sound like that is on the threshold of human hearing. Like, I don't know, maybe the sound of something very quiet, like the rustling of leaves or something, right? Okay, well, we still haven't answered the full question though. So what we've determined is that a rock concert is 10 to the power of 12 times as intense as a sound that basically is 0 decibels in nature. Well, what about a subway? Well, a subway is a 90 decibel noise when it's moving along there. So we could say that 90 decibels is equal to 10 log I over IO. And we could then say that we could divide both sides by 10. And we could say that 9 is equal to the log I over IO. And so now what we could do is we move over here and we could say, well, that means that 10 to the power of 9 is the ratio of the subway in relation to the sound that is barely on the threshold of hearing. Okay, so now let's go ahead and let's just compare the two. So if we take IS over IO, which is I subway over the sound that's barely on the level of hearing, and we compare that to the IR, which is the rock concert intensity. That's an R there, I apologize about that. Right, an IR over IO. We can compare the two simply by taking the relative ratios between them. And what I mean by that sounds more confusing than it actually is, but I can basically take IR over IO and divide it by IS, the subway over IO. The IOs cancel out, and what I'm left with is IR over IO, which is equal to 10 to the power of 12 divided by 10 to the power of 9. Okay, so what we got here is 10 to the power of 12 divided by 10 to the power of 9. And of course, we can simplify this because 12 minus 9 is 3. So what we can say is 10 to the power of 3 is 1,000. And our conclusion is, therefore, the rock concert produces a sound output that is 1,000 times more intense than the sound of a subway. And that's how we would do a question like that. That's comparing two sounds to each other in terms of their loudness, which is measured in watts per meter squared, but is also, I guess, pared down to a decibel level scale that we use. And obviously, to do a question like that, we do need some kind of reference guide. And in this case, I gave you a chart, which was a guide of the various sounds, in terms of their decibel readings. And without that particular chart that you see right here and in the middle of your screen, obviously a question like this would be not really possible. Okay, so thanks for watching.